Hello, this is first part of fifth lecture of linear algebra, and this part is about eigenvectors, eigenvalues, and eigenspaces. Let me start this lecture with recalling a theorem which we discussed in the previous lecture. This theorem is about matrices of a linear operator in different bases. So let me recall you that if we have a linear operator T that maps vectors in n-dimensional space to n-dimensional space, if we fix some basis of n-dimensional space v1, v2 up to vn, then we can relate two matrices to this linear operator. One is called a standard matrix. Here it's denoted by A. This is a matrix obtained in the very simple way. You take your standard basis consisting of vectors e1, e2 up to en. You apply your linear operator to these vectors e1, e2, en. You have n new vectors. You put them in as a columns of some matrix. This is your matrix A. Okay, but now we also can define a second matrix using the basis v1, v2, vn. Precise definition was given in the previous lecture. So here is denoted by B. So B is the matrix of T with respect to vectors v1, v2 up to vn. So we have these two matrices for one linear operator, and you can ask a question how they related. This question is answered by the theorem we discussed in the previous lecture. To answer this question, we have to introduce another matrix. Here I called it M. This matrix whose columns are our vectors v1, v2, vn, vectors in our new basis. Yeah. So if we fix this matrix M, fix these two matrices A and B, then we have the theorem. Matrices A and B are related by this equality. Inverse of M times A times M is matrix B. So small remark, inverse of M exists. Why? Because vectors v1, vn are linearly independent. This is n times n matrix. By one of the conditions for invertibility of a matrix, inverse of M exists, and you have a formula how to find inverse of matrix M. Okay, so we have the theorem. Sometimes it's more convenient to restate it in terms of A. You can say that A is equal to MB times inverse of M. This is the same thing. Okay, so we illustrated the theorem by two examples in the previous lecture. And in both examples, matrix B looked quite simple. It actually, this matrix B in both these examples was diagonal. So we can ask a question, can we find such basis v1, v2, vn such that B is diagonal? And to answer this question, we just have to recall the definition of matrix B. Matrix B is diagonal by definition, if and only if T of v1 is lambda 1 times v1 for some real number lambda 1. T of v2 is vector v2 multiplied by some real number lambda 2, and so on, up to T of vn is lambda n times vn for some real number lambda n. So basically what your linear operator T does, it takes this n vectors v1, v2, and vn, and it scales them. It multiplies each vector by some scalar, by some number. Okay, good. So we have this theorem, and as I already mentioned, we had two examples where B was diagonal, very explicit. Let me recall this example on the next slide, together with one very handy notion we also introduced in the previous lecture. We define what does it mean to be similar for n times n matrices. If you have two n times n matrices A and B are said to be similar if there exists invertible matrix M such that A is equal M times B times inverse of M. So basically this means that A and B are matrices of some linear operator in different bases. A is in standard basis, B is in some other basis. And columns of matrix M are exactly these vectors of new basis. Okay, so this is a very handy definition. You will see later that similar matrices have a lot of common features. So this is why we reserve a word similar for them. And our examples in the previous lecture basically give us these two similarity. So we have this 2 by 2 a little bit strange looking matrix, and we proved in the last lecture that it's similar to matrix 2, 0, 0, minus 1. Diagonal, very simple looking diagonal matrix. And the next example, 3 by 3, this was one of our inspirational examples, basically for the theorem on the previous slide. Yeah, and you see this is a rather complicated 3 by 3 matrix, and this is very simple diagonal matrix. And if you remember the example we considered during the last lecture, we use this similarity. We actually explicitly found matrix M in this example, and we use this similarity to compute the powers of both of these matrices. So basically, if you want to compute power of this matrix, it's quite complicated because, yeah, it's going to be complicated. But to compute powers of this matrix is very easy. Every even power of this matrix is just identity matrix, and every odd power of this matrix is just this matrix itself. Yeah. So we use this fact to explicitly find the formula for the powers of this matrix. Okay. These two examples and this definition and the definition and our theorem on the previous slide brings us to one very important motivational question for the whole lecture. Okay, this question is the following. For a given n times n square matrix A, can we find an invertible matrix M such that M inverse of M times A times M is a diagonal matrix? Yeah, so basically we can restate this question in equivalent form. We can say, can we find a matrix B similar to matrix A that is diagonal? Or is it true that A is similar to a diagonal matrix? Yeah. So we will see later there are several answers to this question. Answer is not necessarily yes, but if answer is yes, of course, the next question is to how to find such matrix M. And basically, theorem on the first slide can give us a clue how to do this. And if answer is yes, we say that the matrix A is diagonalizable. Again, matrix A is diagonalizable if it's similar to a diagonal matrix. Okay, let me translate this question into the language of linear operators. Let me recall from the previous lecture that almost every statement, every question, every definition, every notion for matrices can be translated in the correspondent notation, definition, notion for linear operators. To do this, it's enough just replace matrix A by the linear operator which is given by multiplication by this matrix A. You take a vector V and you map it to the vector A times V. We call this linear operator Gothic T subscript A in the previous lecture. So then if you use this correspondence, that you can translate everything in terms of linear operators. And vice versa, if you have some question, definition, notion about linear operators, you can translate it back into the language of matrices by taking the standard matrix of a linear operator. So let me first translate it into the language of linear operators, this question, and you see that this question is actually simpler a little bit than the question about matrices. Yeah, maybe not simpler. It's, of course, it depends what you consider to be simpler. Okay, so if I have linear operator from n-dimensional space to n-dimensional space, the question is, can we find a basis, new basis of my n-dimensional space, V1, V2, Vn, such that the matrix of T with respect to this basis is diagonal? Or, if you use a remark on the previous slide, so definition of a matrix of linear operator T in a new basis, you can say this, T of Vi is lambda I times Vi. So if you manage to find such basis, such that T of Vi is lambda I times Vi for some numbers lambda 1, lambda n, this means that you answer this question for linear operator. So again, if I just take standard matrix of T, I get this question, yeah, where my matrix M is basically matrix composed of vectors V1, Vn, yeah, and this lambda 1, lambda n, these are just entries of this diagonal matrix. Again, these are two mirror questions. They mirror to each other. They're like twins. It's roughly the same question stated in the different languages. Okay, but now we can use this translation to actually define a very important notion. Look, this vector Vi with this property, it's very special. You take vector Vi, you apply T to Vi, and you get vector Vi multiplied by some number. Yeah, okay. We use this equality to give new definition. Okay. We have linear operator T. We say that a real number, lambda, is an eigenvalue of this linear operator T if T of x equals lambda x for some non-zero vector V. In the previous formula, in the previous slide, these vectors V1, V2, Vn were non-zero vectors because they form a basis, they were linearly independent. So here we consider this as a part of definition. Vector x here in this definition must be non-zero. This is a very important remark. So let me repeat, the eigenvalue of T is some real number lambda such that there exists non-zero vector x such that if you apply T to this vector x, you get vector x multiplied by lambda. Okay, here. And the vector x in this equality, in this boxed formula, is said to be an eigenvector of T. Very important observation. So if x is your eigenvector, if you multiply it by some number, it's going to be, again, eigenvector. And of course, I forget to say, we say eigenvector with eigenvalue lambda. So this is, again, vector x is said to be eigenvector of T with eigenvalue lambda if it's non-zero. And second, if you apply T to this vector, T of x, you get vector x multiplied by number lambda. Okay, good. Let me stress, x is assumed to be non-zero. Yeah, and if you have one eigenvector, you can immediately cook another eigenvector with the same eigenvalue if you just multiply vector x by any number. You can multiply x by 2, because if you T is a linear operator, if you multiply everything by 2, you get T of 2x equal lambda times 2x. Okay, so now, since we started with the matrices, let me translate back this definition into the language of matrices. Let A be n times n matrix, square matrix, yeah? An eigenvalue of A is a real number lambda such that AX equal to lambda times x. AX equal lambda x, yeah, for some non-zero vector x. Crucial point here is non-zero, yeah. And an eigenvector of A with eigenvalue lambda is a non-zero vector x such that AX is lambda times x. Okay, again, this definition is the same as this definition after translation into the language of matrices. These two are extremely important definitions for mathematics, computer science, physics, chemistry, for economics. So if you Google eigenvalue or eigenvector, you're going to get millions of web pages. This is super important definition. You must remember this definition, and we will see in this lecture how to find eigenvalues and eigenvectors. We will give a precise recipe, and we will consider several detailed examples. Okay, let me give one example here. Let me state this example in terms of linear operators. So let me fix a four-dimensional space, and let me consider linear subspace V in this space given by this nice equation. Yeah, This is the three-dimensional linear subspace in R4, and let me remind you, we usually call such subspaces hyperplanes. If it's given by one equation, this is a hyperplane. Okay, so in the previous lecture, in the example class, we described 5 different ways how to find the formula for the orthogonal projection. Because of this, I decided not to consider orthogonal projection in this example, but I could, of course. But I decided instead to consider slightly more complicated linear operator, which you can say orthogonal reflection. So it's basically defined by this formula, where PV of x is a vector of orthogonal projection of x onto V. We found formula for this PV of x in this actually quite similar example in three-dimensional space in the example class. Okay, if you think about this a little bit, you see that this formula is nothing but the reflection in V. So basically you take vector x, you project it orthogonally to V, you have the difference, PV of x minus x, and you add it to your projection one more times. So you basically, when you project, you like hit V, and then you go further by the same vector, PV of x minus x. Yeah. So intuitively, this is just orthogonal projection, and you can consider this as a definition. Yeah. Okay. So let's basically consider the previous question for this linear operator, and you can do it in several different ways. So one way, for example, if you can find the explicit formula for the standard matrix of R by using formulas from the example class from the previous week. So we know 5 different ways how to find formula for projection. If you plug in here this formula, you get a formula for R. And you get standard, for example, out of this, you get standard matrix of our linear operator, of our reflection in V. Yeah, but we can ask, okay, standard matrix you will, if you do this, you will see standard matrix is going to be complicated. Like standard matrix of orthogonal projection, in this example, going to be quite complicated. So for reflection, it's going to be even a little bit more complicated. Yeah, but what we can do, we can use this geometric description of this linear operator to find another basis, such that this linear operator actually looks quite better in this new basis. So its matrix with respect to this new basis is simpler. How to do this? But basically, absolutely in the same way, how we found formula for the projection in the example class. What we can do, we can choose some basis of R4 such that the first 3 vectors are contained in V, and the 4th vector is orthogonal. Then you will see that it's going to be very easy to find the matrix of R in this basis. Okay, I basically guessed 3 vectors, linear independent vectors in this space. Yeah, just quite easy formula equation. So I just took one vector, V1, V2, V3. I took them randomly. They're not orthogonal. They just randomly chosen linearly independent vectors in V. Yeah, and then I need to complete these 3 vectors to a basis. I need to find some vector not in V and better if it's orthogonal to V. But as I mentioned in the example class, if you have such equation, it's very easy to cook up immediately, cook up one vector which is orthogonal to V. You just need to take coefficients of this equation in front of x1, x2, x3, x4, and put them as the coordinates of the vector. So I took this vector V4, here 1, 1, 2, minus 1. These are just coefficients of this equation. And almost by definition, this vector V4 is orthogonal to this V. Yeah, now, if you think about what happened to this vector when you project V1 to V, you just get V1 because V1 is already in V. Again, V2 is projected to V2, V3 is projected to V3, and V4 is projected to 0 because it's orthogonal to V by definition of orthogonal projection. So you substitute this V1, V2, V3, V4 into this formula, and you see that when you reflect V1, you get V1, you reflect V2, you get V2, you reflect V3, you get V3, but when you reflect V4, you get minus V4. And intuitively it's clear, because yeah, it's orthogonal to this hyperplane V, and when you reflect, you just get inverse of V4, just V4 multiplied by -1. Okay, this is a very nice example, which is very similar to example we considered in the example class. But now let me give a non-example. Namely, let me give you the simplest example of a non-diagonalizable matrix. As I already mentioned briefly, not every matrix is diagonalizable. There are non-diagonalizable matrices. Life is not perfect. And if someone asks you to provide an example, this is the simplest possible example of a non-diagonalizable matrix. Again, this is a 2 by 2 matrix. All entries except this one is 0, this one is 1. And you can immediately notice that vector 1, 0, standard vector E1, is an eigenvector. Why? If you multiply A by vector E1, you get 0. So it means E1 is an eigenvector with eigenvalue 0. Okay. Also, if you just decide to multiply A by vector E2, you observe this is equal E1. Of course, you can read this from this matrix. Okay, I basically claim that this matrix is not diagonalizable. Again, how to see this? If you translate this example in the language of linear operators, it basically means that for correspondent linear operator, we should have a basis consisting of 2 linearly independent eigenvectors. Then the matrix is going to be diagonalizable. So if I can find another eigenvector, we already have one eigenvector, E1. If I can find another eigenvector of this matrix such that E1 and this another second eigenvector, they form a basis of R2, then we are done. Matrix is diagonalizable and vice versa. Matrix is diagonalizable if we can find such eigenvector. So let's try to find it. Let's take some vector x1, x2, some other eigenvector of A, and we just apply our definition to this vector. So what does it mean that this vector is eigenvector? It means A x1, x2 is lambda x1, x2. And by definition, let me stress it and repeat, eigenvector cannot be 0 by definition. Yeah, lambda of course can be 0. X1, x2 cannot be 0. Yeah. Okay. So we have this equality, but it's very easy to multiply this matrix A and this vector x1, x2. You multiply and you just get x2, 0. On the other hand, it should be equal lambda x1, lambda x2. Yeah. So we have 2 options here. So if you take a look on the second coordinate, lambda x2 must be equal to 0. So this means that either lambda is 0 or x2 is 0 or both. So if lambda is 0, then we immediately get a contradiction. It means that x2 is going to be 0 in this case. Yeah, and lambda is going to be 0 in this case. Yeah. And this basically means that you're going to get vector E2, but A E2 is E1. Yeah, so you get immediately contradiction. So lambda is not 0, but if lambda is not 0, then x2 must be 0. Yeah, but if x2 is 0, then it basically means that this vector x1, x2 is vector x1, 0. So this is just x1 times E1. So it is indeed maybe another eigenvector if x1 is not equal to 1. But we cannot form a basis of E1 and the vector x1, x2 because they're linearly dependent. Basically, another eigenvector which we try to find is just the scaled E1. It's just E1 multiplied by some number x1. So we need two linearly independent eigenvectors, and this we cannot find. So this explains why we cannot diagonalize this matrix. We will see very explicit result, which you can apply in this case immediately, and to conclude that it's not diagonalizable, but you can do this by hands like this. So there are other methods. We'll consider this. Okay, so not every matrix is diagonalizable, but some matrices are diagonalizable. Okay, now we have to give a new notion. We already defined two new notions: eigenvalues, eigenvectors. This actually German words: eigenvalue, eigenvector. And on the front slide for this lecture, there was a third word: eigenspace. Let us define this. So it's very similar to eigenvectors, but it's a little bit more general. Let me give you a precise definition. We fix a matrix A, n times n, and since I'm going to give definitions in two different languages, language of matrices, language of linear operators, let me also fix linear operator T, and I take any real number, lambda. Lambda is any real number. Yeah. Then I say that the lambda eigenspace of the matrix A is a subset in Rn, which consists of all vectors x, such that Ax is lambda x. You see, this definition looks very much like definition of the eigenvector and eigenvalue, but with a small difference. Namely, here I don't assume that x is not zero. X, for example, x can be zero, and if you substitute here x is zero, you clearly get equality. So this set contains zero vector. Of course, and this is translation of this definition in the language of linear operators. Lambda eigenspace of linear operator T is a subset in Rn consisting of all vectors x such that T of x is lambda x. Again, this is just a subset, and as I already mentioned, both of them contains zero by definition. Okay, and we will see in a second that, of course, these two subsets are vector subsets. So because of this, this explains why it's said to be eigenspace. Okay, so three remarks. So first of all, lambda eigenspace of linear operator T is, of course, the same thing as lambda eigenspace of its standard matrix. Yeah, because if you replace T by the standard matrix of T, you get this definition where instead of A, you have a standard matrix of T. It's basically going to be the same thing. Yeah. So these two definitions are translatable by taking the standard matrix of T. Yeah. The second remark, very important. So you can rewrite this equality. You can rewrite this equality in this way. This is just the kernel of the matrix A minus lambda I. Why? Because look at this. You have this equality, Ax equals to lambda x. Okay, you can rewrite it Ax minus lambda x equal to 0. Then you can put x outside of the bracket. You can say A minus lambda times identity matrix multiplied by x is 0. But this is nothing but the definition of a kernel. So this space is nothing but the kernel of this matrix. Yeah. This immediately implies that these two subsets are vector subspaces. So because we know that kernel of any matrix is a vector subspace. Okay, so they're linear subspaces. Okay, good. So, but again, important remark here that it may happen that this kernel is 0. And actually, we already know when this kernel is 0, when we cannot find non-zero vector x. So basically, by definition, if lambda is not eigenvalue, then this kernel is 0. So it means this eigenspace is 0. So what we just proved, that lambda eigenspace is a 0 subspace, if and only if lambda is not an eigenvalue. Or we can put it into the contrapositive way. Lambda eigenspace is not 0 vector subspace, if and only if lambda is eigen value of matrix A. Okay, good. Let me state it more precisely. We fix matrix A, n times n matrix A, and then we fix number lambda, and then the following conditions are equivalent. Lambda is an eigenvalue of A. Lambda eigenspace of A is not zero. The matrix A minus lambda times identity is not invertible. Determinant of this matrix A minus lambda times identity is zero. Okay, so equivalence of the first two we already know. If we want to see equivalence of 2 and 3 and 4, they immediately follows from a theorem given in the previous lecture about 10 equivalent conditions for a matrix to be invertible. So we know that this matrix is not invertible if and only if its kernel is not zero. So we get equivalence to the condition 2. And another condition which we gave in the previous lectures, that matrix is invertible if and only if its determinant is not zero. Yeah. So we get equivalence of condition 3. Okay. So this is a bit sketchy. I strongly suggest to go over the proof by yourself or read the proof in the lecture notes or in the book. Okay, now if we use these 4 equivalence properties, we can observe that the fourth property is actually very interesting. You see this determinant equals to 0, this condition. We can take this determinant of this matrix and expand it using the formula for determinant which we gave in the previous lecture. So once you do this, you actually get the polynomial in lambda of degree n. And this polynomial looks like this. Its degree, as I said, its degree is n. Its coefficient in front of the top power, the leading term, the leading coefficient is -1 to the power of n. Its constant term, it's easy to find. You just take this determinant and substitute lambda equal to 0 here, and you get determinant of A. So A0 is just determinant of A. Much more tricky to see that the second term here, A n minus 1, so coefficient in front of lambda to the power of n minus 1, it's actually a trace of a matrix A multiplied by -1 to the power of n. Let me recall you that the trace of a square matrix is a sum of diagonal entries of this matrix. Yeah. So this polynomial, it's usually denoted like this: chi subscript A of lambda. Lambda is traditional notation for the variable, for the unknown of this polynomial. And this polynomial is called characteristic polynomial of the matrix A. This is very important polynomial. You should remember its definition. And basically, this definition is just this. You take matrix A, you take some unknown variable lambda, you subtract A minus lambda times identity. So what you just doing, you're subtracting lambda from the diagonal of matrix A, and then you take determinant. Okay, when n is 2 or 3, this is quite easy to write down explicitly. We will see in some example. Okay, so now this proposition basically said that lambda is an eigenvalue of A, if and only if it's a solution of this equation. It basically means if and only if lambda is a root of characteristic polynomial of A. This follows from this proposition. This result is so important, so let me state it explicitly. If you have n times n matrix A and a real number lambda, this lambda is an eigenvalue of A, if and only if it's a real root of characteristic polynomial. So basically, the eigenvalues of A are real roots of characteristic polynomial A. So here's an important point that we assume that the lambda is a real number. Everything in this lecture are about vectors with real entries. matrices with real entries. There's no complex numbers or something. We will discuss complex numbers in the third part of this lecture, but not now. So here's important point that roots of the characteristic polynomial, only real roots correspond to eigenvalues in this part of the lecture. If you consider complex world, if you consider complex vector spaces, complex matrices, then we will see we're going to have the same result for all the roots. But now, in this lecture, only for real. And it may happen that there are no real roots. We will see there are some examples when you have a matrix, you try to find its eigenvalues, you compute characteristic polynomial, and it doesn't have any real root. So it means we have a problem. Yeah, but there is one case when we always can have some real root if n is odd. If n is odd, then characteristic polynomial is a polynomial of odd degree, and you know from calculus, from intermediate value theorem, that polynomials of odd degree always have real roots. Yes, so in particular, if you have 3 by 3 matrix, you always can find at least one eigenvalue. Also, I briefly skipped this corollary, let me repeat it. So the matrix A has at most n eigenvalues, where n is the size of the matrix, n times n. Why? Because fundamental theorem of algebra tells us that every non-constant polynomial has at most n roots, where n is degree. Our polynomial is non-constant because it's leading term lambda to the power of n times -1 to the power of n. So from this follows that your characteristic polynomial can have at most n real roots. Actually, we know from fundamental theorem of algebra that it has exactly n roots counted as multiplicities. So there may be repeated roots, but there are n of them. But some of them may be complex. Okay, so here's an example. You take the same matrix. We basically started this lecture. We consider it into the second slide. And you just compute characteristic polynomial using the formula for the determinant. What you do, you take diagonal entries and you subtract lambda. And then you just use any formula you like. You can expand this determinant by the first column or by the first row, whatever, and you get quite complicated expression. Then you simplify it, you get this polynomial, and this polynomial factorizes like this. So you can see that the lambda 1 is a root, multiple root, multiplicity 2, and lambda equal to -1 is another root. So it has 3 real roots, but one root is repeated. One is repeated root. So I prefer to say it has 3 roots, but one root is repeated. Okay, good. So let's consider the simplest possible example that you can imagine. This is basically was our motivational example. We want to diagonalize some square matrix. But what if the matrix is already diagonal? What can we say about eigenvalues, eigenvectors of this matrix? So, okay, let's just check by definition. If you have a diagonal matrix and diagonal enters lambda 1, lambda n, so then in order to compute characteristic polynomial, you have to basically compute determinant of this matrix. But when you take matrix A minus lambda I, it's again diagonal matrix. But its diagonal enters now lambda 1 minus lambda, lambda 2 minus lambda up to lambda n minus lambda. So what you get, determinant of a diagonal matrix, but determinant of a diagonal matrix is just a product of diagonal elements. So you get a product lambda 1 minus lambda times lambda 2 minus lambda, blah, 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 up to lambda n minus lambda. But traditionally in polynomials, if you have a term lambda n minus lambda, traditionally we revert it, lambda minus lambda n, and for all other roots. So we rewrite this expression in this way, but then we have to compensate it by adding this term. Yeah. So if you can keep it just lambda 1 minus lambda times lambda 2 minus lambda times lambda n minus lambda, then you're not going to have this term. But it's more common to write in this way. Yeah, this is characteristic polynomial of diagonal matrix. And by definition, more or less, it means that roots of this polynomial are exactly diagonal entries. All of them are real. And yeah, so we found the formula for the eigenvalues. And of course, you can use the definition for eigenvector, and you can see that the standard vectors E1, E2 up to n are eigenvectors of matrix A in this case, with eigenvalues lambda 1, lambda 2, lambda n respectively. Yeah. Okay. So here's another example. I deliberately stated it in a little bit obscure, complicated way because I just want to have some break from using language of matrices. Let's just say a few words. Consider one example about linear operators. If you have linear operator T, which is basically a reflection on x-axis, what does it mean? It's a linear operator that maps vector x, y to the vector x minus y. Yeah, then it's you can consider it's a standard matrix. Its standard matrix is just diagonal matrix with entries 1 minus 1. Yeah. So this characteristic polynomial is this, and you can find eigenvectors more or less by definition. If you want to find all possible eigenvectors with eigenvalue 1, you have to find one eigenspace of this matrix. How to do this? You just have to consider kernel of this matrix. Kernel of this matrix is just kernel of this matrix. You just multiply this matrix by x, y, make it equal to 0, and you get y have to be 0. So this one eigenspace is just these vectors. So if x is 0, you get a 0 vector. If x is not 0, you get an eigenvector with eigenvalue 1. All of them are here. All of them are multiple of each other. Yeah. Differs by scaling. And absolutely in the same way you found -1 eigenspace. This is the y-axis. And if you think about geometrical meaning of this example, you have this xy plane and you reflect an x-axis. So everything on the x-axis remains the same. So it's eigenvalues. These are eigenvectors with eigenvalue 1. So eigenvalue 1 means you have ax equal x. So it means vector x goes to x. Yeah. And -1 means vector is reflected. Yeah. So, and then of course, y axis is gonna maps to itself. It's gonna be just reflected. So all vectors in this eigenspace is gonna be multiplied by -1. So they just go like this. Okay, this was nice example. And let me go back to this definition which we gave, definition for similar matrices in the last lecture, and I repeated this definition in the beginning of this lecture. This slide explains why basically similar matrices are called similar, because similar matrices share a lot of common features. Namely, first and most important thing, similar matrices, they have same characteristic polynomial. As a corollary of this lemma, you get that similar matrices have same eigenvalues. Okay, this lemma is not very hard to prove, but you have to accurately write down what is the characteristic polynomial of two similar matrices using definition, and you play around with them. You use a formula, the determinant of product of the matrices. It's a product of determinants of these matrices, and you get this lemma. Strong advice, prove it yourself. If you fail, read the proof in the lecture notes or in the book. Or basically, you just can Google and you find thousands of proofs on the internet. This is absolutely standard result. Yeah. So similar matrices have same characteristic polynomial, same eigenvalues. So it's very tempting to say they have the same eigenvectors and they have the same eigenspaces. But this is not the case. This is not the case, but still we can say something. It's not complete disaster. To say something, we have to introduce a new notion, which useful. So I strongly suggest to remember this. Okay, this notion is called geometric multiplicity of a number. So if you have n times n matrix A and you have some real number delta, by definition, geometric multiplicity of delta is just a dimension of the eigenspace of delta, dimension of delta eigenspace. So how to find the delta eigenspace? You just take a kernel of this matrix, A minus delta I. It's a vector subspace of Rn, so it has dimension. You take its dimension. By definition, this is geometric multiplicity. In order not to say quite often geometric multiplicity, in order to use it later in some formulas, I just here in this lecture decided to denote it by gamma A of delta. This is not something common. This is I just decided to use it in the lecture notes and in this lecture. So you don't need to remember this notation. What you have to remember, this definition. The geometric multiplicity of a number, it's a dimension of this kernel, dimension of the delta eigenspace. So in particular, if dimension of this kernel is positive, if dimension of this delta eigenspace is positive, it means there exists a eigenvector with eigenvalue delta. It means delta is eigenvalue. So geometric multiplicity is positive if and only if delta is an eigenvalue. Okay, this is important. And what is the important thing about similar matrices? That similar matrices has the same geometric multiplicity of each numbers. So we already know that similar matrices have the same eigenvalues. But similar matrices also have the same geometric multiplicities of each eigenvalue. Okay, so this is important. We will use this result later many times. And strong advice to try to prove this lemma by yourself. This is not as simple as this, but the proof is actually quite similar, but a little bit more tricky. But if you fail to prove this by yourself, please read the proof in the lecture notes or in the book. We're not going to prove it now. Okay, let me consider one example. This is a sort of random example. I randomly took matrix A 3 by 3. Of course, I'm lying a bit. This is not a random choice. You will see why. So anyway, I took this matrix A. I just decided to compute everything we defined so far for matrix A. Characteristic polynomials, eigenvalues, eigenvectors, eigenspaces, everything. How to do this? Basically, by definition, you take matrix A minus lambda I, you subtract lambda from the diagonal, you get this matrix. Then let me remind you, this vertical bars, basically a shortcut for determinant. So I took a determinant of this matrix. I compute the determinant using formula, I simplify it, and then I find all its roots, and it turned out to be the roots are 1, minus 1, 2, 3, and then I get this factorization. Of course, here I got lucky, so my polynomial simplifies like this. Usually, if I really randomly choose matrix A 3 by 3, I got some ugly polynomial such that I cannot find its roots using its simple formulas. Its root is going to be complicated. So of course here I cooked up example of A in such a way that all the roots are nice, like integers, small integers. And basically in every example, you're going to find, you're going to solve in this course, I guess 3 by 3 at least, all your roots of characteristic polynomials is going to be nice. Yeah, and there are some simple tricks how to find the roots if you know that the roots are integers. Yeah, so this is not so complicated. We will not discuss it here. Anyway, I found all roots of characteristic polynomial. That basically means my eigenvalues are 2, 3, and -1. Now, in order to find eigenspaces, I already know that delta eigenspace is 0 if delta is not 2, 3, or -1. So it's enough just to find explicitly eigenspaces of 2, 3, and -1. We just do it one by one. By definition, for example, for 2, we take this matrix. Yeah. You substitute 2 here, you get this matrix. And then you just find its kernel. How to find its kernel? You just take this matrix and multiply by the vector x, y, z and make it equal to 0. You have 3 equations, 3 unknowns. You're going to solve it. But remember, by definition, determinant of this matrix is 0. So it means its rank is not 3. If rank of matrix is 3, in this case, then determinant must be non-zero. We found this eigenvalues in such a way the determinant is 0. So this matrix has a 0 determinant, so its rank is 2 or maybe less. We will see it's actually 2. So it basically means 3 equations you got when you want to find the kernel. One of them is redundant. Basically, the rank of the matrix, it gives you the number of non-redundant equations for the kernel. So it's supposed to be like 3 equations. It is actually 3, but one equation is going to be combinations of the other 2. So you can actually get rid of this. So in reality, when you compute this kernel, you have 3 unknowns and 2 equations. So we know by the rank nullity theorem that non-zero solution exists. The kernel is not 0. Yeah, we already know this because of the theorem on the previous slides. Yeah, that if you have an eigenvalue, there exists, by definition, there is a non-zero eigenvector. Yeah, all eigenvectors are non-zero by definition. Okay, so we just solve this system of equations. We found one solution, 1, 0, 1, and all other solutions are just multiple of this by a constant. Yeah, of course, it's clear to see that rank of this matrix is not 1 and it's not 0, so it's not 3, so it's 2. Rank of this matrix is 2, so the kernel should be one-dimensional by the rank nullity theorem. We found one vector. All other vectors here in the 2 eigenspace are just span of these vectors. This gives us a formula for all eigenvectors of A with eigenvalue 2. These are all vectors here except 0. 0 we cannot take. 0 vector is not eigenvector by definition. Okay, good. So we found 2 eigenspace, and absolutely in the same way we can find 3 eigenspace and -1 eigenspace. And this gives us 2 additional eigenvectors with eigenvalues 3 and -1 respectively. So again, this is a nice example. We have 3 different eigenvalues. We have 3 linearly independent eigenvectors. You can check the linear independent vector. How, for example, to check that they're linear independent? For me, the simplest way, you put them as columns of a matrix, take determinant is not 0, you're done, they're linear independent. This also tells you that the inverse of this matrix exists. And of course, this matrix is the matrix we're going to use for diagonalization. You take this matrix M, which I just said, consistent of vectors v1, v2, and v3 as columns. Yeah, you check the determinant is not 0, they're linear independent, you find its inverse, and you write down the formula for M inverse AM. Yeah, this is inverse of M. I've found it using basically the formula we discussed in the previous lectures. Yeah, this is my matrix A, my matrix M. If you multiply, you get this diagonal matrix with diagonal entries 2, 3, -1. And this is illustration of this lecture, and this is illustration of basically the theorem we started with. Yeah, because this is a matrix of the linear operator Gothic T subscript A in this basis v1, v2, and v3. Yeah. Okay, good. We will continue diagonalization topic in the next lecture in more details with more examples. And in the third part of this lecture, we're going to consider briefly similar results about complex matrices, because we're going to need them for real ones for the next week. Yeah, okay, let me stop the recording.